Ladies and gentlemen, our next panel, titled Autonomy in Motion, will be moderated by David Lin, Senior Advisor for Future Technology Platforms at SCSP. Please welcome our speakers Brian Moore, Chief Policy Officer at Bot Auto, and Carl Forsling, Director of Business Development and Strategy at Airbus.
Good afternoon, everyone. I know it's late in the afternoon, and so feel free to, recline those chairs, close your eyes as we start talking about AI and autonomy. My name is David Lin with SCSP. It's my honor to have our two guests with me today. Brian Moore with Bot Auto, an autonomous trucking company, and Carl Forsling, Director of Business Development and Strategy at Airbus. Before we dive into the discussion, though, I just want to share, last week SCSP was on the road. We were in Austin, Texas, and I got to ride in my first ever Waymo, a fully autonomous Waymo, and it was not as terrifying as I was expecting it to be. It was actually quite normal, boringly normal, in fact. How many folks in the audience have ridden a fully autonomous ground vehicle or in the air? Okay, a good number of folks. And this is maybe a good segue into the first question, which is, autonomy, as the audience has shown, is no longer just a concept, right? We're already seeing driverless cars, unmanned aerial vehicles, and project pilots in aviation. In DC, we're going to start seeing more and more autonomous vehicles in the form of ride shares on city streets. And granted, these are just early developments in the broader scale of autonomy, but where would you say, autonomy already delivering tangible value in trucking and aviation? And where do you see big breakthroughs coming? Let's start with you, Carl.
Yeah, for aviation, aviation has always had an element of autonomy in there. Really, since the World War II days, you had started to have autopilots and getting smarter and smarter and becoming more of a capable pseudo co-pilot over time. And we're seeing the evolution of that, to the point where it's not just doing what the pilot says, but also taking some inferences upon its direction. And I think that's one strand in which you're going to continually evolve, right? So you reduce that need for, years ago they took the navigator out of the airline cockpits. At some point you can fill it down to one guy, and and someday in the distant future maybe zero. And then on the other fronts, the logistics of being able to take people out, for military logistics in particular, that's where the most promise is. There are a lot, let's say, regulatory challenges. I think that's where a lot of test cases are going to work out. Military logistics, but then also, in aviation, what they call collaborative combat aircraft. So that'll initially be a robotic wingman with some degree of autonomy. It's doing tasks that's, one, cheaper, it's expendable, and can do things where you're not going to want a human pilot for a lot less risk and cost.
What about you, Brian? Most tangible areas where you're seeing already autonomous trucking delivering value, and where do you see some breakthroughs coming through?
Yeah, so on the trucking side, there's been a ton of progress. So after years and years of testing and testing and testing and promises and promises and promises, you're starting to see real AV deployment. And on the trucking side, you're already seeing it in off-road environments. You're seeing the mining sector. Here in Australia, it's moving goods in, really tough terrain, areas where there's labor shortages, really, tough environments where there's no roads, so mapping is a little bit difficult. So that's already being deployed. It's happening today. There's an autonomous truck probably right now carrying something, whether it's sand or something else. And you're actually already seeing autonomous trucks, and these are big rigs. When I say trucks, I mean Class 8 big rigs, already moving goods, a lot of it in the state of Texas, with a driver behind the wheel, but the autonomy system is active. So that's happening already. But where we're very close to is pulling that driver out, because the technology, and this is happening across a number of companies, not just ours, we've validated the safety case, which means we have enough data, we have an advanced enough simulator, we have processed all of this to reach a level of confidence that we can take the human out of the cab and it will be reasonably successful, meaning it's far and away safer than a human, and it has seen millions and millions of situations that you and I could never see in a lifetime, and it has passed all those scenarios successfully. And that's where we're at. So we're at that point where we'll see these vehicles on the road with no human in it, carrying commercial goods, whether it's your laptops or medical devices. So really what that means for the industry is you're going to get a much more efficient supply chain. There's a huge driver shortage in the trucking side. There's 100,000 drivers that we need today. Even in best case scenario, autonomous vehicles are just going to fill a small portion of that over the next few years. But we're going to have trucks driving pretty close to 24 hours a day. They may stop here and there for maintenance, but a human truck driver can drive a maximum of 11 hours in one day. So it really constrains the routes that they can take. Rural communities are extremely underserved. So we'll see a much quicker supply of goods, but also where they can go. So we start reimagining communities and rural communities and real growth in areas that were previously impossible, because now we can actually get there. So goods moving in a much better way. But really the safety component is probably the most compelling case for everybody here is they're really safe. I mean, you mentioned boring, and boring is how the system is designed. It doesn't need to speed. It doesn't need to text. It doesn't need to, drink and drive or any of those awful things that cause a lot of the issues on the roadways today. So we should see, and we will see, incredible safety benefits, both on the robotaxi side, but also on the trucking side. I mean, half of the fatalities on the road today are either from speeding or drunk driving. So neither of those things should happen in an autonomous vehicle. The system by design should not be speeding for any reason, really. So the safety case is really, really, really compelling. So we'll start to see that reflected in injuries and fatalities on the roadways. But we're also going to see these really awesome efficiencies in supply chain. So it's a very, very exciting time, and we're finally at that point where we're seeing deployment. 2025 and 2026 and 2027. It's going to be awesome.
And along those lines, fast forwarding 5 years from now, what does success look like? What are some of the milestones that you're going to be measuring against, be it on the safety side or on the more on the tech side, on the machine learning side, that you'll be grading yourself against to measure progress? And then what does that progress look like, say, 5 years from now?
For us, I would say I'd use as an example. We have a autonomous logistics helicopter we're developing for the Naval Aviation Systems Command, the Marine Corps, which is designed to carry supplies throughout the potentially the Pacific Island chain, carrying missile reloads, resupply, things of that nature autonomously, and be able to do that 24 hours a day, regardless of weather, not risking a human pilot to deliver boxes of ammunition or food or what have you. And so we're developing that right now based on a commercial aircraft to which we made fly-by-wire, so it takes electronic impulses vice a person moving the controls, and be able to build and deploy that so they can autonomously in a large supply network carry supplies across these island chains autonomously. And that's the sort of thing, really within the next 2 to 3 years, being that's the prototype being developed, and shortly thereafter, hopefully deploying that in mass and really being able to change the game of being able to connect, real time these troops, which previously would require, ships, cargo planes, things of that nature to be put at risk, potentially in a conflict scenario, and being able to do that via autonomous vehicles continuously allows them to have a lot more maneuver space and that really save lives as well as money, resources, et cetera.
Brian, milestones 5 years from now?
Yeah, so on the societal part are we delivering on the safety side? Are we actually seeing this reflected in data? The vehicle should be getting into incidents, per millions of miles at a way lower rate than humans. So we need to make sure that's happening. Otherwise, we need to go back to the safety case and make it safer. So we're always measuring against human drivers. Not only are we as safe as a human driver, but are we way safer than a human driver? Because we should be. The capability is there. There's 360-degree vision. There's no blind spots. Things got a number of cameras, radars, lidars. There's no reason it shouldn't be so much safer than a human. So if we're just about safer, a little bit safer, it's not good enough. So we'll always be measuring against those safety standards. On the business side, and because this is a business, you can't just spend $1 billion to drive a truck autonomously. It has to make sense from a business perspective. So we also measure cost per mile. Is our cost per mile below what it would cost for a human to be in the cab? Obviously, that makes sense for the business, but that cheaper cost also gets passed through the entire supply chain. So even the manufacturer, can charge less for their product because they're paying less on the delivery component. The distributor, the shipper, the end user. So those cost savings get spread across the entire chain. So you're not just seeing a lot of speed efficiencies. You're seeing a lot of cost savings in the industry. So AVs should be saving us all money as well. It's safer, quicker, and it should be saving money. I mean, that's kind of the whole purpose.
Do you know off the top of your head what that cost per mile is for your average like internal combustion engine vehicle? Or
yeah, it goes up and down. I mean, you've seen in the news, like I think there's a pause on visas for new truck drivers, and there's new enforcement standards for English language proficiency. So there's all these pressures that are actually pushing that cost per mile of a human driver up because we're pulling folks out of the system for one reason or another. But it goes up and down a bit, but it's right around $3.50. So and autonomy is at a point where it's right near that, or even just a bit below. It just needs to perfect some of the the domains and lanes that it intends to drive on. But the cost per mile is very close.
Is there an aviation equivalent to that, Carl?
Yeah, there is. I mean, and you see it really across the industry on both commercial and military sides. So one of the biggest labor expenses for an airline is pilots, as well as military aviation. The pipeline of qualified and eligible people in the early 20s is always becoming more problematic. And those people both are taking a long time to train. At least a year, generally far more than that, to become proficient and really useful for jobs, and the time, that's all gets wrapped in the cost, it gets wrapped in the time. So yes, there's a huge amount of savings from the personnel side and the training side. The promise of autonomy has always been fewer people in the system, and up until this point, before we truly had AI at it, it was always almost additive. Use a military example, your Reaper, which is a surveillance drone, you always have an operator and a system and a sensor operator, communications people, behind them, maintainers and all that. You're actually adding people, even though you're adding autonomy. And now that we have, agentic AI, and you one to many is a possibility, the scale and your reach has really gone up quite a bit.
So behind every real-world deployment, there are real engineering challenges. I was wondering if each of you could talk a little bit about the hardest technical challenges that your companies are grappling with right now to deploy your autonomous systems. Be it like perception, machine learning, trying to emulate human decision making behind the wheel or in the cockpit. Why don't we start there? Brian, do you want to kick us off there?
Sure. Yeah. I mean, edge cases are always an interesting topic. How are you accounting for, what if a camel runs across the street or a couch falls out of the sky? It's like, maybe we didn't put that, in our calculation because it's not something you can really predict. There are these scenarios out there, and edge cases do occur on the roadways. They may be extremely rare, but you do want to account for those. So when we think about our safety case and how we're validating these edge cases, it was previously very very difficult to get all of those scenarios into a simulator and kind of run your model against it. But we're at a point where all of that has gotten way more efficient and way more cheaper, and this is a result of computing and the cost of annotating data. So you can now kind of plug in all these crazy scenarios that you're probably never going to run into, but you can actually map against it and see if it's going to solve for that. So, I mean, that is a challenge, was a huge challenge, but we're getting to a point where we can actually solve for that challenge. So that's a good thing. You want autonomous vehicles to be considering these very, very rare scenarios, even if they are highly unlikely to be encountered. So we're at that point.
Carl, hopefully you don't run into pedestrians in the sky, but what happens?
No, but it's not, and it's very interesting you said that, because in some ways it is a more predictable environment. There's no, small child running out into the roadway in the sky. But at the same point, there's sort of an old expression that's aviation is not inherently dangerous. It's just more unforgiving of, carelessness and neglect. So the consequences of something going bad in really any sort of air, whether there's people on board or not, can go catastrophic, pretty quickly. So design the safety architecture and being something that's can be evaluated on a consistent and, from both a airworthiness standpoint and a regulatory standpoint. When you have for example, a kind of system that's black box, how do you figure out what that failure rate is? Is it going to make a mistake once every 100,000 hours, once every million hours? And lots of things in aviation are dictated upon these safety standards, which are based upon replicable standards, for safety reasons. And you have to build that engineering in there and make sure you can validate all these decisions. I'd say, interestingly, perhaps not the most difficult challenge, but I think one that's kind of interesting, and I don't think we always talk about it, is that human-machine interface point. For example, when you're talking about a robotic cargo aircraft, for example, In a real aircraft, there's whether it's a flight attendant or a crew chief in the military or somebody, when you're loading cargo, that person is directing that process. So when a guy who has no experience with tech at all, who's driving a forklift, the guy's pointing him here, making sure he's safe, make sure he doesn't do anything wrong, make sure he doesn't break anything. When it comes to an empty aircraft, how do you make that obvious to him what he's supposed to do? And that carries through to the maintenance, to the operation, all that. One guy doing a silly thing can destroy $1 million asset very quickly. So you have to make it's dummy proof in a lot of ways.
And that's a good segue into my next question is how do your respective technologies fit into today's infrastructure? Like beyond the vehicles themselves, how do your trucks or aircraft fit into like the highways, the logistics hubs, the airports, the air traffic control system, both from a regulatory perspective, but from just a physical infrastructure perspective? What needs to evolve there, either on the platform side or on the infrastructure side, before we can reach a more like ubiquitous scale?
So there's, that's a huge topic. Obviously there's that regulatory framework, goes that safety and reliability piece. All these systems have been built over 100 years, designed around systems that have lasted that long. And aviation, just like some other fields, is very cautious, and rightfully so, has that need for safety throughout the process. But being able to document that properly, integrate it, and assess it versus, humans have their own intrinsic failures, be that drinking and driving or just errors that may actually be greater than a machine's. But how do you assess that? The other is how does it interact with the environment? So it's one thing in aviation. That's one of the big things. When we test aircraft, you have to have airspace set aside for you because in the United States there's a great amount of uncontrolled airspace where people can literally fly through without talking. So how do you detect and avoid those things? Obviously, there's that part of that's a sensor issue, but part of that's a policy regulatory issue of what those other aircraft's responsibilities are to do with the drone. Then there's the infrastructure that carries all the way through to when you take off and land. How do people cross the runways? How do people taxi around mixed amongst traditional stuff? It's actually going drone to drone is an easier interaction than drone to machine or to human, because they talk different languages, basically.
And not all aircraft have the same comms either.
Correct. And that's a process. The FAA has been trying to modernize for manned aircraft for literally decades at this point. And now another thing is getting added to that mix, and we're going to have to adapt very quickly to make this viable in commercial aviation.
Brian, we were talking a little bit about this backstage too. What are your thoughts on this? And to add to that too, when it comes to communicating software-defined vehicles, whether or not you're talking to, in your case and Auto's case, truck to truck, but ideally when it's more widely deployed, all autonomous vehicles are talking to one another, not just one of the same company, right? I don't know if you have any thoughts to share along those lines.
Yeah, no, a lot of thoughts. It's a really great question, because we can think about where we can go in terms of making this all more efficient and better, and data sharing more efficient for all of us. But so we have to design our vehicles for the roads as they are today. We can't rely on changes. We can't rely on state governments and federal governments, for many reasons. So we design our vehicles to be able to operate, in the conditions today. So you can think about, for autonomous vehicles, like how do they get pulled over? How do they do a roadside inspection? How do you get a citation? Who do they talk to? So we have to design, and we work very closely with state law enforcement, state department of transportation to come up with like first responder interaction. So our vehicles need to be able to recognize that they're being pulled over. So it needs to be able to see, the light sequence, needs to validate that it is indeed a police officer, not a bad actor with a fake light. So then there's the remote assistant back at mission control that can maybe validate to the vehicle what it's seeing, because we can see what the vehicle is seeing, like back at home base. We've got the cameras, we've got live footage, so we can say, yeah, that is indeed a cop. But the vehicle needs to also play its role and recognize those scenarios. And then when it comes to interacting with law enforcement, it requires some training and interaction with them and learning from them. But a lot of the information can be outside the vehicle, like your registration or your bill of lading. Like there's no reason it has to be inside the cab. So we can place some information outside of the vehicle. Maybe there's a lockbox. There always needs to be a 24-hour number that they can call if they need to actually speak to somebody live. But there's all these things that we can do to actually navigate these challenging, situations as long as we work with local partners. So I think we've really gotten to a good point on first responder interaction, being able to recognize not just COTS, but emergency vehicles, knowing when to pull over. So it's really the sensing and perception that has gotten a lot better to be able to recognize these strange scenarios. But there's other areas where we need policy changes, like way stations. Like an autonomous truck has a hard time going into a way station, which is a really dynamic environment. Maybe the person who needs to inspect the vehicle says, "Oh, don't go in this lane, or am I going that one, or am I go back to that one?" It's not great for an autonomous system. So we need to come up with a way where autonomous vehicles can bypass that. And there's a lot of great progress on this exact topic, working with the Department of Transportation on how do we come up with a mechanism where autonomous vehicles can get the information that regulators need and law enforcement needs, but doesn't need to actually go to that traditional way station that truck drivers currently have to go through. So that's something that's already in progress. When it comes to kind of vehicle to vehicle or V to X, like V to a larger system maybe maintained by the government, we don't have it today, and we can't rely on it, but you can imagine a scenario where these vehicles talking to each other would be hugely beneficial. So if we're sending 10 trucks from Houston to West Texas, and they're all 100 miles from each other, and the first vehicle encounters an edge case or a construction site or something crazy on the road, you'd want that information to go to the other vehicles as well, so they can maybe detour or just recognize that there's going to be some road hazard coming up. So that's where we need to go, is vehicles talking to one another. So there's a connectivity component to it. I mean, in my West Texas example, connectivity is not great. So we can think about infrastructure build out and improving connectivity, and that's not just for autonomous vehicles. There's benefits to everybody to have greater connectivity. And then speaking with centralized databases, like what we see on the road, it would be very beneficial for everybody here and for state agencies if we see like a massive pothole or something crazy happened on the road, or God forbid, a horrible accident in a very remote area that nobody else has seen and law enforcement hasn't been contacted. That's information that we should be able to provide to regulators or law enforcement. So there's so much data collection happening on these vehicles that is very valuable for you and I and for regulators. So there should be like a centralized system, and that's the V to X component that I mentioned. So that's an area where I think we'll go, and there are conversations around that. We're not there today. We don't have great vehicle-to-vehicle connectivity or data sharing, and certainly not with state agencies. And it goes in the other direction, too. I mean, if a state agency knows about a construction site, I mean, that should go to vehicles, whether they're autonomous or human-driven. So there's a lot that we can do there to improve roadway infrastructure.
Now, Carl, all of this has dual-use implications, right? And in many cases, I think one of the first fully autonomous systems to be deployed were autonomous drones or surveillance drones for military reconnaissance. And so in that sense, like DoD led this commercializable technology. Can you talk a little bit more about that dynamic and that phenomenon?
Yeah, so there has to be a business case, and whether that's government has a much different one than business. Trying to make a autonomous aircraft viable on the commercial side is an entirely different endeavor, and honestly, there's a lot of miles between here and there on the commercial side. But the military's use case, where it's less sensitive to the economics, at least on a daily basis, where it has a little is in an environment, a combat environment, or a oversea environment, something of that nature. Less sensitive to loss of the platform, in the performance of its mission, and something has to get through, but you don't want to risk human beings for it. So that use case lends itself to being a little bit more forward-thinking and being able to use autonomy and be able to adapt it, accordingly. On the commercial side, you both have to make an economic case for the platform you're using, whether that's traditional helicopter, traditional airplane, has to make money just on the maintenance and fuel per hour, but then the autonomy has to pay for itself too. And you have to get through all the regulatory hurdles, the safety hurdles, and all that. All that is to say that that day will come eventually on the civil side, and this thing is particularly vertical transportation, when you think about the air taxi type of environment. But that technology is probably going to be validated first on military, then on logistics, carrying things, potentially first in remote areas, and only then, once you validate a safety case, are you going to be able to even fly over populated areas unmanned, and then at some point in the future, perhaps people. But there's a lot of technical regulatory, safety, cultural challenges that I think just like many other technologies, like the internet itself, that was paved by the military first, the use case matured, and then it became economically viable and borne out for civilian use.
So we've talked about safety at multiple points, but wanted to bring it back to that for just a minute. Public confidence in autonomy often comes down to one question, is whether or not it's safer than a human. How do you measure and demonstrate safety in ways that regulators and everyday people can trust and have confidence in? On the military side, I guess this equation's kind of reversed, I guess. You send in autonomous drones or autonomous systems into dangerous environments where you could save a life instead.
Yeah.
So you could kind of talk about both sides of that coin.
Right. So it goes beyond just the literal, one for one. Obviously, you're eliminating a pilot or crew or other person that could go into an environment. You're taking them out of that equation. It allows you to do things you might not otherwise be willing to do because you're losing a machine versus a human being, which is inherently different, right? So that's the military's goal in doing that, as well as just using people for other things. This is conceivably a labor saver. But when you talk about the other side, putting in commercial use, but even for military use, that there are established standards for this sort of thing. You have to be able to quantify that. And in aviation, they have what are called design assurance levels. So when you're building your architecture, what's the weakest point in your chain? And depending on whether you are, could conceivably harm people, the standards go up. So, you might have a failure rate of 1 in 100,000 hours of operation for something that might impact a person, but it should be no more than 1 in a million hours of operation before it could possibly kill seriously injure or kill someone. And you have to make sure there are no weaks in that chain. And more importantly, with the AI becomes more difficult is how do you quantify that? How do you simulate the runtime so you can actually validate, like, this is safer than a person? And then there's that cultural piece where you always want to have person, involved in the process. And some of that's a cultural shift, I think, might be generational. The idea that, look, most aviation mishaps honestly come down to, and I was a military pilot, in some way there's human error involved. Almost always, even if there was something that went wrong, it was somewhere in there's a human's error did that. And that's not to say today a machine would do better, but at some point, that's the real, that might become the weakest part in the chain. And we have to look at, when do we make that decision to decide that the machine is the right tool, or is that machine a co-pilot or a wingman to that human, and the human makes the final choice? At what point in the chain does that person need to be? And we're comfortable with both from a numerical, quantitative standpoint, but also, culturally, what authorities are willing to trust to a machine.
Mm-hmm. Brian, on the autonomous trucking side, trust and safety, we've talked about this a little bit already. A lot of the autonomous rideshare vehicles today are precluded from going on highways because of the high speed, and obviously a human passenger is in the vehicle. For autonomous trucking, no passengers, just cargo, but these are large vehicles careening at large high speeds down the highway. How do you build public trust in that?
Yeah, so I mean, for autonomous vehicles generally, I think it's three things. Number one is, the general public needs to be able to touch it and feel and interact with it, and that's hard to do on the trucking side. But there are kind of pass-through benefits from robotaxis being deployed. You're seeing in public polling when these robotaxis roll out, the cities that they're in, the public support goes up like very, very quickly because they get inside it. They're like, oh, this is pretty boring. I can start to trust this robot that's driving me around. So people do get comfortable, and that does have pass-through for the trucking side as well, as people just generally become more comfortable with autonomy and autonomous vehicles. The other part is just proving it out, like show the data, be transparent. And on the vehicle side, it's easier to compare because we have human drivers now. We know what the fatality rates are. We know what the injury rates are. So if you can show the data, and if I can put a plug for the Autonomous Vehicle Industry Association that we're a part of, they do a fantastic job of showing, like, here's how many tens of millions of miles have been already driven autonomously on public roadways, and here's how many accidents they were involved in, and here's how many fatalities they were involved in. So making it just easily digestible for the general public to just see very clearly, here's the data. And so you can prove that it's safer. Here are the metrics. And then the third piece is, like, just are there regulations? And do the regulations enforce safety and compliance with those safety standards? And right now we have a bit of a gap. So we have this patchwork approach where there is no federal framework for autonomous vehicles. We don't have that. So we live and die by the states that we operate in. So autonomous vehicles might be legal in one state, illegal in another state. A version of it is legal here, a version of it's legal there. So it's really inefficient. You need a federal framework. And that will help, because that, baked into those regulations, there should be a certain metric and a certain standard and a certain type of safety case that you should have, and you need to go and prove that to the U.S. government and abide by these regulations. If the public knows that that's in place, they should feel a little bit safer and comfortable that the government's involved in this. So right now we don't have that federal framework, so we really need to work with Congress and regulators on getting that in place. The industry wants it. The general public should want it. It's going to make adoption smoother. It's going to make it safer. And also, just if we want to lead in this technology, you need good policies in place. If you don't have policies in place, you're not going to get the capital going to these companies. Without the capital, these companies aren't going to develop the tech and flourish. Without those companies, you're not going to get the supply chain vendors developing sensors and components for these industries. So you're just going to see this kind of slowdown in the industry while other countries kind of take off and lead in the space. So it all starts with policy. You've got to get your act together in DC so we can thrive.
Before we run out of time, Carl, I just want to give you the last word here. If there were to be a bumper sticker that you want to leave with this audience, and I think that was a good one to end with for you, Brian, but Carl, what's your bumper sticker there?
My bumper sticker, I guess, would be something along the lines of, autonomy, aviation and autonomy are intrinsically a lot together. And, over time, we've gone from, the beginning of aviation, the safety was frankly abysmal. And over the course of years and years of development and standardization of methodically going through procedures and having a solid both regulatory framework and solid best practices in industry, really gotten to a point where, flying is the safest means of transportation. And I think the next level of that is incorporating a higher degree of autonomy, and it really starts, with a combined approach with government, both the civil and defense side, as well as industry, to nurture these technologies that are essential towards, U.S. allies, and continue to dominate in this field, and also, so that both the civil and military sides are continuing to become safer, more useful, and more productive.
Great. Well, we're out of time. We could spend hours talking about this, but please join me in thanking Brian and Carl for joining us today. Thank you.
Thanks a lot.
Oh, sure.
Thank you.